Okay, this is the fourth video in AP Physics C on velocity and derivatives. The last three, we learned all about the derivatives. We learned what the derivative is. Basically, it's a way of finding the slope of a tangent line at a particular position. And we have also learned a bunch of different derivative shortcuts, ranging from the very easy, derivative of a constant is 0, to the somewhat more complicated, like the chain rule. Now we're going to get back to physics. All this derivative stuff we've been learning, dx dt, tells us the instantaneous velocity of whatever particle we're dealing with. So velocity is equal to dx dt. Now when we get to average velocity, we're going to use the old equation. V equals delta x over delta t. The difference between these is the limit. And the best way to illustrate the difference is with a graph, x versus t. Let's say our graph looks like that. We could describe that as speeding up, because you notice the slope here at the beginning is basically 0, and the slope up here at the end is larger. So if we wanted to find the instantaneous velocity at this time t, we draw a tangent line, and the slope of the tangent line equals v. Now if, on the other hand, we wanted to find the average velocity over the whole interval, we'd take the endpoint and the beginning point, and we draw a line between them, and the slope of this connecting line is equal to the average velocity. So the average velocity is total distance divided by total time. Instantaneous velocity is displacement over time, but for a very, very small interval. Now, there's another term you've heard, and it means very similar things to velocity, that is speed. The basic difference between speed and velocity is that speed is a scalar. Now you should remember from last year that scalar means that it does not have a direction, while velocity is a vector, meaning it has a direction. For instance, if your velocity is 3 meters to the second to the east, that's a vector because it's got a magnitude, 3 meters per second, and a direction, east, your speed is just 3 meters per second. That's normally not a terribly important distinction, but there is one important case, and that is when you're dealing with average speed versus average velocity. Average speed is the total distance traveled per unit time, while average velocity is the total displacement divided by the total time. And so it hinges on this difference between distance and displacement. So an example, someone running around a track, it's a 400 meter track. The distance traveled would be 400 meters, and so the average speed would be some number, let's say 5 meters per second. But the average displacement is 0 because the displacement only deals with the distance between the endpoints. So displacement is distance between endpoints. So if we have something that goes in a circle or an oval, like a track, distance might be 400 meters. But displacement, which is the distance between the start and the endpoints, equals 0 meters. So just keep that distinction in mind. There's a couple problems where you'll need to use it. So here is an example. You drive from San Antonio and you end up in Houston. Half of the time you drive at 55 kilometers per hour, and the other half of the time you drive at 90 kilometers per hour. The question is, what is your average speed? Now the average speed, remember, is total distance divided by total time. And in order to do this, we'll have to know that the total distance, or the distance in the first half, delta x, is equal to 55 times delta t over 2. So your speed times the time for that first half. In the second half, delta x equals 90 times delta t over 2. So your speed in the second half times that time in the second half. And that means to get the total distance, we have 55 times delta t over 2 plus 90 times delta t over 2 . And that means the average velocity is 55 over 2 times delta t plus 90 over 2 times delta t, all divided by delta t, which cancels out of the top and the bottom. And so we get 55 plus 90, all divided by 2. And with the calculator, that works out to be 72.5 kilometers per hour is your average speed. Notice that if we assume that you're moving in a straight line the whole time, the average velocity would be the same as the average speed. If you're not moving in a straight line, then all bets are off. Now let's say on the way back, you drive for half the distance at 55 and the other half at 90 kilometers per hour. You might think that the answer would be the same, 72.5 kilometers per hour, but that's not the case. For this one, you'll have to imagine the first half time, and remember if we go from the equation v equals delta x over delta t, the first half time equals the distance in the first half, delta x over 2, divided by the velocity in the first half, 55. And the time in the second half is equal to half the distance divided by the speed in the second half, which is 90 kilometers per hour. And so delta t, the total delta t, is delta x over 2 times 1 over 55 plus 1 over 90. I skipped a number of algebra steps there. And that means that delta x over delta t, which is your average speed, is equal to that. Delta x we can get rid of. And so after quite a bit of arithmetic, wait, that's not right. Yeah, that is right. Equals 68.3 kilometers per hour. The question is, why is this average speed slower on the way back? The best way to think about that is that you're no longer doing half the time at 55 kilometers per hour. You're now doing more than half the time at 55 kilometers per hour because you've got that, it's half the distance. But the part of the distance, the distance you're doing 55 kilometers an hour, takes a lot longer than the half of the distance that you do at 90 kilometers per hour, so it lowers your average speed. Last part of the question now. What is your average velocity for the whole trip? The answer to this is 0, because you end up where you started. And so your displacement is 0. Last of all, we'll graph x of t for both directions. So x versus t. Now on the way there, so here is San Antonio, here is Houston, here's the halfway point, here's the time to get there, and there's the time to, or half that time. So you do the first half of the time at a low speed, and the second half of the time at a high speed. On the way back, it takes you a bit longer, but you go with the first half of the distance at a low speed, and the second half of the distance at a high speed. So that's roughly what the graph looks like. For tomorrow, question 1 and problem 3 will be what I will be checking in your homework, and those are both from chapter 2.